Hi everyone, Assalamualaikum warahmatullahi taala wabarakatuh. So today we will proceed to lesson 6, sample introduction technique for gas chromatography and sample pre-concentration using solvent evaporation. So this lesson is divided into two sections. The first one will cover the sample introduction techniques and the latter cover the type of solvent evaporation method. So in the previous lecture, we have been discussed a few topics of preparation of organic compound in either in solid form and also in liquid samples. So most of this technique are using organic solvent to extract and collect the analyte of interest. Okay, for example, we use dichloromethane, we use methanol, we use hexane to extract and concentrate the organic compounds such as a polyaromatic hydrocarbon, a pesticide from soil or water matrices. So after the extraction, the sample will be introduced into GC or HPLC through liquid injection. So the final sample is in liquid forms. So today we are going to discuss the automatic sample preparation technique, usually equipped with gas chromatography. Okay, this is our learning outcome for today's lessons. So in the first section, students should be able to describe sample introduction techniques of volatile and semi-volatile compound prior to gas chromatography analysis. And you should be able to explain the concept of headspace, push and trap, and thermal desorption technique. Okay, headspace, push and trap, and thermal desorption technique. So in the second section, students should be able to identify and discuss a few methods available for solvent evaporation, such as a rotary evaporator rotor web, centrifugal evaporator, Cordona Danish evaporator, and nitrogen blow evaporator systems. Okay, let's start with the first section. So there are various introduction techniques for gas chromatography. When talk about gas chromatography, so it is actually involve the separation and detection of compound that can be vaporized or volatile. So these volatile compound are present in the atmosphere, in the workplace, on industrial settings, need to be monitored with regard to the safety consideration. For example, volatile organic compounds such as BTEC. BTEC stands for benzene, toluene, ethylene, and xylene in drinking water. So for the sample in drinking water, we can directly measure using headspace. Or we can also track via push and trap method prior to analysis. Meanwhile, BTEC in the atmosphere can be tracked on the solid support material and introduced through the gas chromatography through thermal desorption method. So there are few here. The first one is liquid, the second one is SPME, the third one is headspace, the fourth one is a push and trap, and the final one is the thermal desorption method. Let's start one by one. Most of the samples is introduced to GC in liquid form after you conduct some sample extraction technique. So you will come up with the liquid form of samples. So after sample preparation, such as you using liquid extraction, solid phase extraction, and the final product is in liquid form. So the liquid will be injected to GC using micro syringe with the capacity is around 10 microliter. Usually there are other two, despite of a liquid injection, there are other two type of injection method, which is headspace and SPME. So the SPME has been covered in the previous lecture, but we just recap again. In SPME, the analyte is absorbed into fiber coating material, while in headspace, only vapor phase was analyzed. However, the vapor phase is representative to the original samples. This is SPME. It's involved two stages. The first one is absorption and the second one is desorption method. So the analyte is absorbed onto a fiber coating material, either in the form of solutions or headspace. Then it is thermally dissolved into gas chromatography injector for analysis. For headspace, is the method of analyzing the vapor phase in a thermodynamic equilibrium with a sample in a closed systems. Okay, it actually indirect determination of volatile constituent in a liquid or solid. So this method is not analyzing the original sample, but only measure the vapor phase. Okay, in thermodynamic equilibrium, the concentration of analyte is representative to the analyte in original sample. Okay, the method involves a sample incubation in an oven at certain temperature and pressure to achieve the thermodynamic equilibrium before injected to GC column. During thermodynamic equilibrium, the analyte concentration in the vapor phase is representative to the original sample. Okay, another technique of sample introduction to gas chromatography is push and trap method. So this method is widely used for extraction of volatile organic compound from aqueous samples, from water, from wastewater, from industrial effluents. Okay, the volatile and semi-volatile analyte are pushed out from the matrix, such as water, by using inert gas, usually nitrogen, then trapped or collected in a solid solvent material, usually TNAC and activated carbon. So after that, the solvent is then heated to release the target compound into the GC for analysis. So there are three methods actually in the push and trap method. The first one is sample purging. The second one is analyte trapping. And the third one is disruption of analyte for analysis. So during the sample purging, so the aqueous sample, typically around 5 ml, is introduced into the U-shaped glass purging vessels. So then high purity of nitrogen gas bubble are passing through the sample to push the volatile analyte into the carbon or TNAC trap. So typical flow rate of nitrogen usually 40 to 50 ml per minute and around 10 to 12 minutes. Okay, the disruption. Okay, the third step is the disruption method. Yeah? The push and trap method is then followed by the disruption method. Okay, the disruption step, the trap is heated around 180 to 250 degree, and then backflush with nitrogen to send the sample to the GC column. Okay, typically the disruption time are 2 to 4 minutes with nitrogen flow rate of 1 to 2 ml per minute. Okay, you can see the diagram here. Okay, the first one is the purging the sample and then trap into the TNAC or activated carbon trap. After that, backflush with the nitrogen to push the volatile organic compound into the GC column. Okay, next we proceed with thermal desorption method. Actually, thermal desorption is one of the last component in the push and trap method. The role of thermal desorption in conjunction with gas chromatography is to dissolve the analyte from the tube or collecting material by application of heat and then analyze them by chromatography. So volatile analyte in the atmosphere can be absorbed onto tube or solid support materials. So you can see the tube here. Okay, these tubes are used to concentrate the volatile compound, for example from air sample in the environment or workplace. So in this manner, air sample in the atmosphere can be regularly monitored. So by placing the inlet of the tube at the suspected source of contaminants, a measured volume of air is pulled through the tube containing the solvent by using an air sampling pump or vacuum pump. Okay, after the monitoring is done, the tube is bring back to the lab for analysis. The tube is then inserted into the GC thermal desorption unit, where the analyte are then dissolved directly to the gas chromatography by flowing the nitrogen over the samples. Okay, this is the diagram show how thermal desorption is pushed to the GC column. Okay, that's all for the technique of sample introduction to gas chromatography. We have five. We have a liquid injection, solid phase micro extractions, headspace, push and trap method, and finally thermal desorption method. Okay. Now we proceed to the next lesson, which is the pre-concentration method using solvent evaporation. Okay, there are few type of solvent evaporation available in the lab. So the purpose of solvent evaporation is to pre-concentrate the sample. So pre-concentration is concerned with the reduction of larger volume of sample into a small sample size that available for analysis. Okay. Okay, the most common approach for solvent evaporations are rotary evaporator, rotary, centrifugal evaporator, condenser Danish evaporative concentration, and nitrogen blow evaporator, nitrogen blowdown evaporator. So in all case, the evaporation method is slow, very time consuming, and with a high risk of contamination from the solvent, from the glassware, and also from the blowdown gas. Okay. Let's start with a rotary evaporator. Okay, a rotary evaporator or rotovap is found in almost any organic chemistry lab and has a great way to quickly evaporate most volatile organic solvents. It is typically used when evaporating a single volatile sample at relatively larger volume of samples. So typically, a round bottom flask is used where it is lower in a heated water bath, and then the flask is rotated. It is rotated to increase the surface area and provide an even transfer of heat. Okay. Okay, the sample also is placed under vacuum to lower the boiling point of the solvent. Okay, a rotovap work by placing the sample under vacuum, thereby lowering the boiling point of the solvent. However, since the glassware is under high vacuum, there's always a risk of solvent superheating and boiling over or bumping. So once the sample boil over, there is a high risk of cross-contamination and losing of analyte. So there's also a safety concern regarding the glassware. If we use improper selection or defective glass, it will lead to an implosion. So it also can only handle a single vessel, so we cannot evaporate multiple samples. So if you have a few samples, you have to do it in series, which can be very time consuming. So I also attach here a video from YouTube regarding a rotovap system. I hope you can see a clear picture how we use a rotovap to evaporate the samples.
Okay, so now we're going to look at rotary evaporation. So we've got this solvent and we've got our compound in the solvent. We need to get rid of the solvent. So we use a rotary evaporator, such as one of these, and we're going to place our sample in the flask. The flask goes on this end here, and it will be clipped. And essentially what we have is a distillation setup. So we have the flask here, we use a water bath to raise the temperature, and then we have the vacuum over here. We have a condenser here to cool the solvent that's coming off, which will then be collected in this trap here. Over here, at this point, we have a tap which allows us to bleed air into the system. So in order to set it up, first thing we're going to do is make sure we switch it on. And here we can then set the temperature. Essentially, for most organic solvents, we're going to want 40 degrees. That will do very nicely. And then we're going to turn on the cooling water. So it doesn't want to be too fast. Just running through the system. You do want to make sure that the receiver flask is empty. It should have been emptied by the last person, but just check that, because the last thing you want is to, if your compound accidentally bumps and is pulled up over into this flask, you don't want to be contaminated with anything anyone else has been using. So we're going to pour our compound into the flask, and then we're going to carefully clip the flask in place. Okay? Be particularly careful with heavy solvents such as DCM, because they are very dense and that can cause this to fall down. So we're going to make sure that this tap here is open, and then follow the vacuum through, around, and we're going to turn on the vacuum. And we can hear that now. So you can hear the vacuum hissing away. And now we're going to start to rotate the flask, and we're going to turn it till it's about 2/3 1 o'clock position, keeping our hand underneath here just to make sure that it can rotate gently against that and it's not going to fall in. And then we start to close the tap. So we're turning that tap so it's closing, and keep an eye on that solvent so we can see it's starting to evaporate. So this is dichloromethane, which has a very low boiling point anyway. It's a boiling point of 45, so it doesn't take much. And now you can see we've got the tap closed. It's rotating, it's bubbling away nicely, and you can see on the glass there's condensation starting to form from evaporation. Once that's going like that, we then slowly use this to lower the flask just so the bottom portion now is in the water bath. You don't need the whole flask in the water bath, just that bit. And we can see it starting to evaporate. We can turn up the speed. The reason why we're rotating the flask is to ensure that it increases the surface area as the solvent's rotated and flung out by centrifugal force around the sides of the flask. And it also means that as it's evaporating, it also stops it from boiling and bumping. And that's when essentially it jumps from this side over to here because the vacuum's built up and the solvent explosively evaporates very quickly. So we're going to leave that to evaporate nicely. It's there, evaporating away. Okay, so we've got to the end of our evaporation, and we can now see that all the solvent has evaporated, everything's gone. We'll slow that down, stop, and then we're going to raise it up out of the bath. Next thing to do then is to open this tap, and it'll help release the vacuum, and we can go and switch the vacuum off. Once the vacuum's off, we then are going to unclip, remove, and then you'll want to give the flask a wipe with some blue roll in order to have a dry flask. One very important thing to remember is that if you are preparing a sample, is to weigh the flask before you put anything into it. And that means you can weigh the flask again afterwards with no weight, and you can get the weight of the solid that's in your flask. Final thing to do then is switch off, and then take the receiver flask, unscrew, remove this, and if there's any solvent in here, there isn't in this case because DCM is very low boiling and the house vacuum is very high. It's a very good vacuum. but it's to make sure you do empty anything that you've collected in the receiver flask out of here. Put this back on, tighten the screw, and there we go.
Okay, the other type of solvent evaporator is centrifugal evaporator. So a centrifugal evaporator is a great way to evaporate a large number of samples at once, since it can accommodate multiple centrifuge time at a time. So just like a centrifugal evaporator also works under high vacuum to lower the boiling point. However, instead of rotating the glassware, just like the samples are placed in a multiplex heated compartment where they are centrifuged to avoid bumping. So, the centrifugal evaporator is not suitable for higher boiling point solvents such as water or DMSO, because it can be time consuming, typically overnight. So additionally, care must be taken by the operator to ensure that the sample are well balanced, okay, and a proper centrifuge tube are used. So the improper glassware tend to break the centrifugal force. So this can be quite problematic when working with precious sample or hazardous materials. Okay, another pre-concentration method is Danish evaporator. This Danish evaporator condenser was developed by Julius Hyman and Company, USA. Okay, the system consists an evaporation flask, usually 500 ml, connected to one end to a cinder column and the other end to a concentrator tube. Okay, you can see here, the above one is the cinder column and the bottom one is the collection tube. The collection tube usually around 10 ml. The sample containing organic solvent around 200 to 300 ml is placed in the apparatus and heated with a water bath. So the temperature of the water bath should be maintained around 15 to 20 degrees C above the boiling point of the organic solvents. The positioning of the apparatus should allow partial immersion of the concentrator tube in the water bath and allow the entire lower part of the evaporation flask to be bathed with hot vapor or steams. Okay. In Danish evaporative system, the vapor then rise and condense within a narrow opening cinder column. Okay. In this situation, sufficient pressure need to be generated by the solvent vapor to force their way through the cinder column. Initially, large amount of condensation of this vapor return to the bottom of the Danish apparatus. Okay, this returning condensate continually washing the organic in the evaporation flask and assist in the process of recondensing the volatile organic. So the process concentrate the sample to approximately around 1 to 3 ml in 10 to 20 minutes. Okay, escaping solvent vapor are recovered by using a condenser and collection device. Okay, the last type of solvent evaporation is by using nitrogen or gas blowdowns. Okay, in this method, a gentle stream of high purity purge gas, okay, such as nitrogen, is passed through over the surface of the sample. The sample may be contained inside a conical tip or glass vessels. So in this situation, the purge gas is directed toward the side of the vessels and not directly to the top of the extract in order to induce a swirling action. Okay. So the extract containing vessel may be partially immersed in a water bath to speed up the evaporation process. So this is I also attached a video from YouTube regarding the nitrogen evaporation system, so you can see a clear picture. So this is my references.
The nitrogen tank has 3 knobs that you can adjust. 1, 2, 3. I labeled them this way so that you would do them sequentially. Number 1, when you turn this on, which may be hard to do, then this needle should go up here showing you the quantity of gas in the tank. Number 2 is the pressure adjustment. It says please don't adjust. It's set to a reasonable value. You should not need to change that. Number 3 is the flow. This is a needle valve. It's sensitive. As I turn this, I'm increasing the flow of gas. The nitrogen will flow out of this syringe tip here. I'll have to feel it to adjust the flow rate appropriately. So I've taken off my gloves so I can feel the wind. Turning on the flow. So I can feel that on my hand. It's a nice gentle stream of wind. That's what I want. Up here we have a bubbler tube that will enable you to see the rate at which the gas is flowing. So that's a very slow rate. And that's clearly a much faster rate now. So this rate is about right for evaporating dichloromethane. I can feel the gas on my hand, and it's a nice gentle wind. Here I have a vial. It's got a little less than a milliliter of dichloromethane in it, and I will evaporate this using my stream of nitrogen. So here I've got the vial, here I've got the nitrogen stream. You can hear a little whistling as the wind goes through the opening of the vial. I can see ripples on the surface of the dichloromethane as it is being evaporated by the wind. It gets really cold here, so it's getting foggy because moisture is condensing on the outside. It's probably less than 0 degrees Celsius. So to evaporate more rapidly, I'll use the heat of my hand to warm up the solvent while I am blowing nitrogen onto it. A little agitation can help increase the evaporation rate. So it's very cold. Through the glove, I can feel the cold. While I do this, I should have the hood fan on. I have it off so you can hear me better, but when you evaporate solvents in the hood, the fan should be on. Sometimes at the end, it can be hard to evaporate the last drops. As the solute concentration increases, the boiling point is elevated. Okay, so this looks pretty good here. I've just got one drop in the corner. Get rid of that. Warm it up with my fingers. I am done. When you turn off, I recommend you do in the same order. Turn this off first. This dial will drop. Don't touch this one. And turn off the flow rate.
Then, thank you. I think that's all for this time. In the next lesson, we will discuss the chromatography method. So please be prepared. So, Assalamualaikum warahmatullahi wabarakatuh. Thank you and see you again. Bye.